Okay, I'm getting better at timing this. So if I had probably 30 more seconds, that would have been perfect. The last bullet that I wrote down, I was just saying that we need to perform more trials. So not only do we need to perform more trials, one data point isn't good enough, but those trials can't be the same thing every time. You wouldn't just put the same mass on there and get a different time. No, that is not useful, okay? Let's get some more masses on there. Let's change the mass and see how the period changes. Again, the reason that we're doing this is so that we can get a wide range of data, because we know if we change the mass, the period should change. The spring constant should stay the same. Okay, so we are trying to perform more trials with increasing mass each time. Again, notice that I have not done anything except, the only thing that I've done, the only thing, I haven't written down any analysis yet. This is simply procedural experimental steps. The analysis comes next. So if they split up a question like this, please make sure that you actually read this, because you guys get confused on this a lot. Everyone gets confused on this a lot. Procedure and analysis are two different things. If you're doing calculations, that is analysis. Procedure is about what you are doing with to get the data in the first place. So I'm going to erase this. I'm going to move on to analysis. And again, I think I mentioned on the last one, there's probably something else I could have done using conservation of energy, maybe from the top of the hill to the bottom. Yeah, I could do it that way. What I'm focused on is showing you an application of something you have just learned. This is another way that we could have done it, okay, what we just showed you. Alright? So that's why I chose to do it this particular way. So now that we collected the data, we have a bunch of masses, we have a bunch of times for a set number of oscillations. We want to determine the spring constant. So what we need to do now, first thing, we don't actually know the time for one oscillation yet. We have the time for a number of oscillations. So the first thing that we need to do is determine the time for just one oscillation. Thankfully, that's really easy. Okay? We're going to divide each time by the number of oscillations that happened while we were timing. Okay? That will give us the actual period of oscillation for this particular mass in this particular spring. Okay? So first thing, we get the time for one oscillation, just the regular old period of oscillation. And let me remind you of the equation that we were using. We were doing this. The period for a mass on a spring is 2 pi times m over k. So, I have always urged you, when you can, make a graph of something and linearize. Okay, I know you hate to do it, but this is really how science is performed in a lot of cases. We get data points and we try to linearize them, at least at like the lower levels. If you guys go into college, if you're going into a science major, knowing how to linearize stuff, and that's expected of you in class, like, trust me, your professors are going to be blown away that you know how to do this. Okay, this is a good skill to know. So, there's a couple different ways we could do this. Probably the easiest, if you don't want to deal with the square root, what could we do? Okay, if you don't want to look at that square root, couldn't we square both sides? If I square both sides, well, I'm going to get the period squared over here, and then 4 pi squared times m over k on this side. Now, if you don't want to square it, that's fine. You'll have to do this just slightly differently. The reason I'm squaring is a lot of people don't like square roots. They get really thrown off by square roots for some reason. Okay? Exponents are different. They're like, oh, exponents, sure, whatever. People get thrown off by square roots. I'm just trying to help you avoid them. So, looking at this equation, your variables are the mass of the cart and the period of the spring. The period of the spring happens to be squared here. The constants are 4 pi squared and k. So again, let's do some rearranging. Let me write this a little bit nicer. Here, I'll just do this. 4 pi times k times m. Same exact thing, I just switched where things were. Well, guess what? M, that's your independent variable. It's kind of like your x variable, okay? This is your dependent variable, kind of like your y variable. We know there's an equal sign in here. There's nothing getting added on, so there is no like plus b term. Okay? There's none of this. This is a 0, this is b, which leaves this right here, 4 pi squared over k. Well, that must be what the slope would end up being if I were to graph the period of this oscillation squared versus n. Same linearization process we've done in the past. Okay? Same exact thing. So, we are graphing this. Graph period of the spring squared versus m. And the slope will be equal to 4 pi squared over k. At this point, all we have to do, find the slope, plug into the above equation, that one right there, where you actually find the value of the slope, and that value is equal to 4 pi squared over k. And finally, you solve for the spring constant. That is one way to figure out the spring constant. Like I said, there's probably another way, another 2 or 3 ways. This is the method that I thought of, because this is what I was interested in teaching you about. Okay, this right here. But this isn't even the problem that we originally set out to solve. This was one step on the way to that. So, I'm going to erase this now. It says, now that the spring constant has been determined, describe how the final speed of the cart just before it hits the spring could be found. So now we know the spring constant. Great. Okay, now we know the spring constant of this spring. We found it using a kind of neat method. So now what we're going to do, we're kind of writing out, now we're combining procedure and analysis. We're going to combine them all into one step, because it's almost like I'm fitting 2 problems in one. Be sure to list any equipment that will be needed, how that equipment will be used to collect data, and how that data will be used to determine the final speed of the cart. So, okay, let's think about what sort of equation we could use. And I said earlier, you know what, there's not 2 objects colliding into one, it's one object that's just compressing a spring. I know I used the word collision earlier, it's not really a collision between 2 objects. If the spring, we're assuming the spring doesn't have mass, then we can just call this, we can say that it is I guess almost like even though we have the cart sticking to the spring, not necessarily any energy lost here. Because that spring, we are assuming, even though we didn't really say this, is massless. Okay? So, this is, I guess, before cart hits spring. And this is after that happens. Right before the cart hits the spring, there's a lot of kinetic energy. At the end, there is elastic potential energy right after the collision, okay? Or not right after the collision, I should say, when it has compressed as much as it's going to. So, we know that this is 1/2 mv squared. Now we know v, that is, or now we know, not v, excuse me. Now we know the spring constant. That is important, okay? That's going to stay the same in each trial. We do some simplification here. We can cross off the 1/2. Here's what we're left with. We are trying to determine v. We can change the mass. That is our variable to change. And if we change the mass, so it's kind of like our independent variable, our x variable, if you will, that's going to change how much the spring compresses. That's what this equation says right here. It's not going to change the spring constant. It will change how much the spring compresses. Also, Well, I'll get to that in a second. So, let's see. How much the spring compresses, that x, that's kind of like, that x squared, that's kind of like our y variable. So if this is our y variable, let's get this by itself. We need to get that k out of here. I'm going to do a little bit of rearranging, but if x squared is our y variable, we bring the k over to the other side, we get m over k, nope, excuse me, v squared over k times m. Sorry, I wanted to make sure that we had, this is our variable. I didn't want to mix it in with our constants. Okay? M is our variable. Our independent variable. X squared is our dependent variable. K is a constant. And if we're always releasing the cart from the same height on the hill, then the speed at the end should be a constant as well. Why is that? Well, and you can write this down if you want to. So at the top of the track and the bottom of the track, energy should be conserved. At the top of the track, there is only gravitational potential energy. At the bottom, there's only kinetic energy. mgh equals 1/2 mv squared. The speed at the bottom should be equal to the square root of 2gh, a result you've seen many times. Changing the mass, doing multiple trials by changing the mass should not change the velocity. Okay? It shouldn't change the velocity. So that's good. Velocity should be a constant here. That's the whole goal of this. We're trying to compare, we're trying to see if our prediction of the velocity is accurate. Because if it is not, then we might be able to say some things about this collision. We might be able to say, oh, well, there's a lot of friction involved, and we thought it was frictionless, it's not. Or maybe that spring actually has some mass, and that collision is not as elastic as we thought. Okay? So we should be able to say the velocity is constant. And if we are to do this, if we were to make a graph of the mass versus x squared, how much the, x squared versus the mass, how much the spring compresses, squared versus the mass. You know what? I'll save it for a little bit. Let's do the experiment. Let's list the steps, the things that we need to measure first. So, most importantly, we need to make sure that the starting point is the same for each trial. We always need to make sure that cart starts at the same exact spot. Okay? That's very, very important. For each trial, measure mass of cart with our triple beam balance. That takes care of us finding out what m is. Next, we let the cart go down the hill. Until it hits the spring. And then what do we do once it hits the spring? We look really, really carefully. We put a meter stick alongside the spring, maybe start the 0 right where the spring's ends, where the end of the spring is that's going to hit the cart. And then, as it compresses, measure how much it compresses. Let cart move. Then measure max compression. With a meter stick. Measure the maximum compression with a meter stick. Okay? That takes care of x. Those are our two variables, m and x. Almost everything else is just, well, analysis now. I guess we will put in the last point of, again, we don't just want one trial of this, we want multiple trials. For multiple trials, we're going to change m. I'm going to stop there, probably do one last video, then we'll be done.